today we're going to be doing reverse chain rule for senior advanced. Before we've done normal chain rule for derivatives, where if we had a nested or a composite function, which is basically a function within another function, we would use something called a chain rule, where we would take the derivative of the inner function, multiply that by the entire derivative of the outer function with the derivative, with the normal inner function inside. And if you guys have no clue of what I'm talking about, make sure you go watch the chain rule video. Anyways, it's the same case for integrals. So far with integrals, we've only been doing the normal antiderivatives. We've had our rules and then we've applied those rules. Well, now we're going to need to learn how to do it when it comes to composite functions. And for that, we have something called I like to call it the reverse chain rule, and its more common name is U substitution, and you'll see why in a second. So for this to work, we're going to need to use this little theorem thingy. So basically it says if U is equal to g of x is our inner function within a whole function. So basically it would look like the integral of f of g of x dx. If g of x is our inner function and f of x is our outer function, and we want to find the integral of this, what we're going to do is we're going to set u is equal to g of x. Then that means du is going to equal the derivative of g of x times dx, and the integral of f of u times du is equal to f of u plus c. So let's see how that works with an actual example. So we have evaluate the integral, definite integral of indefinite integral. These ones are indefinite. If it's definite, that means we find a number because it has an upper and a lower limit. Anyways, so this is an indefinite integral, and we have the function, the square root of 2x minus 1. So if we look at this again, we notice our outer function, or f of x, is going to be the square root, and our inner function is going to be 2x minus 1, and then we have our normal dx. So what we're going to do is we're first going to set our inner function equal to u. So g of x is going to equal u, which is 2x minus 1. So then we're going to take the derivative. So g of x, is going to equal du, which is equal to 2 dx, because it's going to be the derivative of g of x times d of x, and the derivative of 2x minus 1 is 2 times dx. So then we're going to take what we have here, du is equal to 2 dx, and we're going to solve for d of x, and we're going to get d of x is equal to du over 2 because basic algebra. So now we're going to take what we have here, du over 2 is equal to dx, and how u is equal to 2x minus 1. We're going to take both of these and substitute it, or replace it in this normal function. And once we do that, we're going to come back here and get the normal one of the indefinite integral of the square root of u times du over 2. So then we can simplify and solve normally now. So we're going to bring the over 2 out because it's a constant. So we can just bring the 1/2 out in front. So we have the 1/2 times the indefinite integral of the square root of u times du. And then we actually solve normally, and then we get 1/2 times the u to the power of 3/2 over 3/2 because of our integral power rule, plus c is equal to 1/3 u 3/2 plus c. And then we substitute in, because we have that u is going to be 2x minus 1, we're going to substitute in here. And we're going to get 1/3 times 2x minus 1 to 3/2 plus c. Another example, we have evaluate the indefinite integral of cosine of 2x times dx. So first we're going to find our inner function. Our inner function is going to be 2x, and our outer function is going to be the cosine of something. So we're going to take our 2x and we're going to set that equal to u. Then we do our next step, which is finding the derivative of said u. So we're going to get du is equal to 2 dx. So then we solve for dx, we get that dx is equal to du over 2, and then we substitute our values here back into here, and we're going to get that the indefinite integral of cosine of u times du over 2. We're going to bring out the 1/2 because we can do that. It's equal to 1/2 indefinite integral times cosine of u dx, and then we're going to simplify more, and we're going to get 1/2 sine of u plus c, and then we actually substitute our value for 2x, and we get 1/2 sine of 2x plus c. So then the next part of this lesson is going to be real life examples. Well, we've already done real life examples of derivatives, and that is optimization, where we would have something like you have Farmer Joe has 200 feet of fencing to run, and he wants to know what's the maximum area he can have. Well, remember how we use derivatives for that? Well, that's basically how we apply real world problems and derivatives. So calculus isn't completely useless. So we've done real life examples of derivatives, but what about integrals? Well, we actually do have real life examples, and one such real life example is the following. Firemen spray water on a house fire. The spray rate steadily increases until it reaches its maximum capacity, 24 gallons per minute. It takes 100 minutes to put out the fire. The graph shows the spray rate as a function of time. How much water do the firemen use to put out the fire? So we have our little graph given to us, and we have our max here, which is going to be 24, so let's just write that again. And it's rising steadily up until the 20-minute mark. So we're going to write 20 minutes here. And we know that it takes them 100 minutes, so we're also going to add 100 minutes here. So how do we find this? Well, let's look at the graph a bit. We have our y-axis being gallons per minute, as in per minute, how much are we shooting out? And down here, we have the minutes. So if we think about it, the amount that's being shot out is going to be the gallons per minute times the time. But if you think about it, the gallons per minute times the time is basically going to give you the area underneath the curve. And if you go back to what we learned before, we know that the area of the curve can be solved by definite integrals. And we could use rhyme and sums, but we're not going to do that. So basically, the idea to solving this is to find the area underneath this curve. It's not really a curve, but we're going to call it a curve. So let's do that. We can't really find a specific function for this, so we're going to break it up into two parts. So if we find the function of this first one, we're going to get 6 over 5x. That's a beautiful x. And then we have our function for this, which is just going to be a plateau, and it's just going to be y is equal to 24. So now we put it into definite integral form. So for this section, we're going to have our lower limit be 0 and our upper limit be 20. And why is that? Because it stops at 20. So we're going to put it into our notation. And then for this chunk, we're going to use our lower limit of 20 and our upper limit of 100, because we can't add it at 0, because this graph only starts at 20. So we have that as well. So now let's solve the actual integrals. We have the definite integral was upper limit 20, lower limit 0 of 6/5 x dx. So then we find the antiderivative, and we get 6x squared over 10. Remember, since we're using definite integrals, we don't need the constant. And then we write our little notation so we don't forget the upper and lower limit. And we solve and get 240. We do this, we repeat the steps. We get our antiderivative be 24x, and then upper limit 100, lower limit 20, and we get 1,920. So we're just going to add 1,920 plus 240 to get our answer of 2,160, meaning that our firemen shot out 2,160 gallons of water. Don't forget to subscribe and like. If you have any questions, you can email info@agoramatrical.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email, but without the info and the end. So bye!